I guess I should improve, be nicer to people. So we just had an excellent ITC colloquium by Daryl Haggard, and she will talk about something else in a few minutes. We'll start with our own James Guillochon. Should there be a French pronunciation to your last name?
Yes.
How?
Guillochon.
Okay. I'll try it next time. And he will speak about the dark year for tidal disruption events. And then we'll hear from Daryl, that is visiting us from Amherst. Must have been a difficult drive this morning. And she will talk about the deep Chandra X-ray limit on the Putative intermediate mass black hole in omega 7. And then we'll hear from the CFA colloquium today, Andrew MacFadyen, that is visiting us from New York City, from NYU. He's on sabbaticals in New York City as well. And he will talk about top-heavy jets. And finally, we'll hear from Ofer Cohen from the CFA, who will talk about the interaction of habitable M-dwarf planets with stellar wind of their host stars. James.
Thanks, Avi. Oh, great, it's dark now. Perfect. So I'm going to be talking about a project that we posted to the archive a couple weeks ago that I primarily did with my former advisor, Enrico, who I cannot escape because he's on sabbatical here this year. So let's just get right into it. So first I'll just talk about what I think we know well, which is the prompt fallback rates onto a black hole after the tidal disruption of a main sequence or white dwarf or any kind of star, really. That's something that simulations have cataloged for a number of different parameters, and I think we understand that fairly well. And I'll talk a little bit about how, if you can reliably link that to the accretion rate onto the black hole, how you can use that to potentially measure black hole masses, which might be a nice way of measuring quiescent black hole masses, which we may not have a very good handle on. I'll then talk about how in simulations, hydrosimulations, you find that it's not so simple, that it can be hard to take the material that's ripped from the star, circularize it quickly, and convert it into light that you can observe. I'll propose that the solution to this is general relativity. And I'll talk about how adding spin to that picture introduces a dark year for tidal disruption events, and I'll explain what that is shortly. Okay, so this is an ensemble of simulations that I ran in a paper that I put out a couple years ago. It's just a polytrope, different impact parameters shown here with the different colors. This just verifies that you get fallback curves that roughly fall as t to the minus 5/3, which people have calculated and known since the late 80s, and multiple other authors have come to the same conclusions now. And in this phase, general relativity likely has some influence on the prompt fallback rate, but it's maybe a factor of 2 in the accretion rates and time of fallback. So I think we understand this fairly well. And honestly, there's not too much reason to do pure Newtonian disruptions anymore to learn very much new. So why is that interesting? Well, we have these fairly basic scalings that depend on black hole mass, star radius, and a function that depends on stellar structure and beta. That function we found did not depend very heavily on either impact parameter or stellar structure. And due to the fact the mass-radius relationship for stars is close to 1, it turns out that the timescale over which tidal disruption events peak is pretty constant over 3 orders of magnitude in stellar mass. So that means if you observe a stellar tidal disruption and you measure what time it peaks, in principle you can very reliably determine the mass of the black hole doing the disrupting. So that would be very powerful, and it could teach you a lot about the demographics of black holes. And if we just make that simple assumption that the fallback rate equals the accretion rate, and we put the various thermal flares that have been observed thus far, in addition to the jetted events that have been observed, and then we just draw random events, and we ask which ones are peaking below and above the Eddington limit, And we find that things are actually matching pretty well. The events lie very nicely on the expected distributions. There are upper limits and lower limits involved just because we don't necessarily know the peak luminosity if we don't catch the peak. But everything seems roughly consistent. The main thing we don't know is there could be a lot of light that's lost in a phase that we're not observing the flares, and so in principle the luminosities could be higher. But everything seems to work fairly well, assuming things are prompt, which is interesting. So what's the problem with all of this? Well, if you do a Newtonian calculation, which is what's shown here, and you disrupt a star, the naive assumption has been that material will circularize here at twice the tidal radius once it returns to periapse very quickly. You can see that that's definitively not the case when you just have pure Newtonian effects involved. Matter is sprayed out to large distances from the black hole. It takes a long time for it to actually circularize and accrete onto the black hole. So if there is no additional source of dissipation, then tidal disruption events are slowed down by orders of magnitude potentially. So on the left I'm showing just a simple calculation from Canizzo where we start with a ring at a certain radius and we let it viscously accrete onto a black hole for different alpha parameters. And you can see here that things that are started out, say, at the tidal radius or are accreting onto the black hole on timescales of a decade or 100 years, so extremely long timescales. On the right, I'm showing the result from a simulation that did include relativity, but very, very mild degree of it. And it's comparing the fallback rate, which is the black curve, to this blue curve here. What you can see is that the blue curve peaks at much longer timescales, about a factor of 10 longer than the fallback does. And the accretion rate is reduced by about a factor of 10 as well. So this would not look very much like the tidal disruptions that we have been observing thus far, which seem to peak in sort of month timescales. So if you don't have relativity, and you just draw the path that this stream makes as it wraps around the black hole repeatedly, it makes this very nice elliptical spiral, which looks something like this. And what's interesting about it is that there is absolutely no stream intersections in this structure. It just wraps around and around, missing itself, presuming that the stream had no width. That'll be important later. But it doesn't actually intersect at all. So there's not really a way for it to dissipate energy when you completely ignore precession that might come as a result of GR. If you add GR, so now here we're just adding de Sitter precession around a non-spinning black hole, then the picture starts to change. So left to right, we're showing black hole masses from 10 to the 5 to 10 to the 7. Because the tidal radius scales to a weaker power of the black hole mass than the Schwarzschild radius does, the relativistic effects get stronger as you go to higher black hole masses. So as you can see in 10 to the 5, you have some precession. That elliptical spiral is starting to overlap. And as you move to 10 to the 7, things really start getting complicated. It recesses by almost 90 degrees every single time it returns to periapse. The angles of intersection are quite large. And the structure starts to get a bit complicated. So if we actually just ask what kinds of events are going to be dissipative or not, we find that there's really kind of two extremes where the events can be dissipative. One is when the mass ratio between the star and the black hole is not too extreme, so maybe a stellar mass black hole plus a main sequence star. The reason being is that the velocity, the internal velocity of the star is comparable to the periapse velocity. So every time it returns to periapse, it dissipates on order v star squared, and that's comparable to the binding energy. So you can circularize relatively quickly in those low mass ratio systems just from hydro effects alone. As you go to very high mass black holes, the stream starts to become very, very narrow and doesn't dissipate so much energy every time it returns to periapse. And if you actually calculate the pure hydro dissipation, it's 1% or less per orbit. It's very, very tiny. What you rely upon there is that things must precess into one another and collide. And when you do that, you can circularize relatively effectively, shown in this movie here from Bonnero in 2015. And you actually do circularize quite effectively at scales that are much, much smaller than the scales you saw in the pure Newtonian calculations. An additional complication here is that the majority of black holes are likely spinning. This is just a cumulative distribution function of black hole spins. I don't necessarily believe this particular one. The point is, though, is that they're not all at zero. They have a range of spins. And a lot of people think that the spins may be biased towards higher values rather than smaller values. So what does the spin do? Well, it introduces an additional precession term, frame dragging or nodal precession. And what that does is it takes the material and precesses it out of its original plane. So you take the pictures that we had in the earlier movies, and now you can imagine that the stream gets torqued out of its original plane. Now, rather than intersecting itself, it forms a complicated three-dimensional elliptical spiral that doesn't necessarily intersect with itself right away. So this was kind of taken to its extreme in this paper by Jane Dye in 2013, where the thickness of the stream was presumed to be very, very thin. You can see after the material is wrapped around for 10 or 100 or even 1,000, which almost certainly never happens, but it forms this very, very complicated structure. So just to recap, for, say, low mass ratio encounters, GR is relatively unimportant. It's just the pure hydro that dominates the dissipation. When you move to supermassive black holes, the GR does become important, and it can cause the stream to self-intersect. This is more important the higher in mass you go. The streams get thinner, and spin can drag it out of the original orbital plane, causing them to miss. So hydro simulations have shown this effect for the spin, causing it to miss. And so this is the very first paper, I think, that shows this, led by Hayasaki. But these are expensive. You don't want to run a million of these. They take too long. So we went with sort of a cheaper approach, a heuristic approach, which I can describe in detail to you later if you so desire. But it allows us to construct thousands of these systems and ask about their statistical properties. So this is just zooming in on periapse, looking at the variety of stream-stream intersections that you get, and to stop making you dizzy. Basically, there's three primary subclasses here. It really just depends on how does the stream intersect itself. Does it intersect itself at a very high angle, dissipating a lot of energy, or is it a very grazing angle, where the two streams are almost meeting it in a parallel direction? Depending on how acute that angle is, you can have a lot of dissipation or little. And this leads to either the flare being prompt or slowed. So slowed events will be slowed down by factors of 10 or 100. They may not look like TDEs. They would peak on too long of a time scale for you to actually identify them as such. So that's just shown here in this cartoon. So on the top, we have a situation where it can be prompt. The intersection angle is large. Originally, it follows the original fallback rate. And as you increase the viscous time by making that angle more and more narrow, you slow down the flare progressively more and more. The secondary effect is that there's a delay in the amount of time it takes for the stream to finally reach that first self-intersection. That turns out to be roughly 1 year. So hence the title of the talk. So when you do this statistically, we find that maybe 10% of events are prompt. They would look like normal TDEs for low mass black holes. And then a fraction increases to maybe 50% at the higher mass end. The delay time also scales as black hole mass. It's typically a year for 10 to the 7-ish, but it can be shorter or longer depending on the mass of the black hole. And so this is the final plot I'll show. The fallback curves are the dashed line. This is just basically if you presumed the accretion rate equaled the fallback rate. And the color histograms are showing now if you add this slowing correction. So I would argue that the ones that you would identify as being TDEs are the green ones, the ones that are prompt. And what you also see is that the ones that are slowed are really slowed down a lot, decades, 100 years for them to peak. And it's only a small fraction that are prompt. So in summary, I think a large fraction of TDEs are going to be slowed by this large factor. There can be a dark period of about a year, which may delay the amount of time between the prompt signatures, such as the shock breakout and gravitational wave emission, and the thermal flare. And the key is really, where does the stream self-intersect? And so the final point I'll make is that this may alleviate the tension in the rates that we have for black holes. Theoretically, it's estimated that the lower limit on black hole disruption rates is something like a few per 10,000 years. But observationally, we find it's about a few per 100,000 years for thermal flares. and a few per million years for jetted events. This may be explained by the fact that a large fraction of TDEs actually are not prompt. They're slowed down to the point of not being able to recognize them. And I'll stop it there. Yes, I agree with that. Yeah, totally.
So the test would be different surface.
Yeah.
Questions for James?
So James, to some extent, the whole idea of measuring the mass function of black holes with TDEs is complicated by this effect, right? Because what you're saying is that there's a mass dependence to the appearance of these objects, and therefore we might get the bias to just a high mass.
Yeah, that's quite possible.
Sure, but this is, it seems like it's somewhere between 10 to 7 and 88 where you don't get this delay, and for lower masses, these TDEs might not appear as transient. So
Yeah, I mean, there's if you look at the histogram, there is kind of a separation in the sense that at the low mass end, there's a big separation in time. The ones that are slowed tend to be peaking around decade timescales, and the ones that are prompt are peaking in months. So that might be a way to distinguish between the ones that are actually, say, following the fallback rate directly versus the ones that are significantly slowed. But I agree with you that this muddies up the picture, makes it a little harder to make the direct connection. There's a...
If we had some other signature of your TDE that was more prompt, and since the delay time depends on the black hole mass, could we use the delay time itself to measure the black hole mass?
Yeah, I think in a statistical way. I think one of the interesting bits here is that depending on the exact angle the star comes in, you could have a stream hit or a stream miss. And it might be even a change in 5 degrees. That's enough to change that outcome. That being said, all sky X-ray survey looking for the shock breakout signature would be great because actually directly from that you can get the properties of the star and the black hole, and you can make some estimate as to when the thermal flare would follow it.
We need to move on. Thank you very much. I was asked to comment that when you throw out your dishes, make sure that you recycle the ones that are not dated.
I have a loudish voice. Is that going to work? Can you guys hear me all right? Okay. Great. So I'm going to be talking today. Today is my day of talking about non-detections for anybody who saw my last talk. So here we have another non-detection. So this is a deep X-ray limit on the intermediate mass black hole that has been claimed in the globular cluster Omega Centauri, primarily based on dynamical work. And I'm going to start talking about the X-ray data that our team collected, and then I'm going to show you again at the end some very nice new work. So I have a special thanks here to Laura Watkins, who kindly fueled me with a few of her slides that were presented 2 weeks ago at the Black Holes and Dense Stellar Clusters meeting. And so I'll show you that the tension between the dynamical measurements and the accretion idea about how to track this intermediate mass black hole in Omega Centauri remains, even though we thought that we had put it to rest, but it's not to rest yet. So here's Omega Centauri. This is a beautiful image of the Hubble data that has been collected on the globular cluster. As you probably know, it's an extremely enigmatic stellar cluster. It has multiple stellar populations. It may be a stripped dwarf galaxy remnant, so maybe not a proper globular cluster at all. And it has been reputed to host an intermediate mass black hole or not. So there are many multi-wavelength observations, including those in the X-ray, which I'll be talking about today, Chandra, XMM. The HST data, I'll show you a very brief graphic of how that has been used to tile the cluster. We have nice radio data. Fermi's looked at Omega Centauri, et cetera, et cetera. So we see multiple stellar populations and also get dynamical measurements out of the optical data. In the X-ray, what we're trying to trace is accretion, and when you're talking about the binary systems, you talk about both accreting and chromospherically active objects. So earlier this morning, we were talking about RS-CDN stars. Indeed, we have a population of those residing here in Omega Centauri and other galactic globular clusters. The radio and the gamma ray observations probe millisecond pulsars and jet from systems. So I won't be talking about this very much. There is a Fermi detection in Omega Centauri. We've never been able to find any radio detections of pulsars in Omega Centauri, and so that's sort of an interesting missing population, which we see to be sort of ubiquitous in other clusters. In particular, 47 Tuck has a large population of millisecond pulsars. So just to focus in here on the intermediate mass black hole. So in the dynamical modeling, you need some sort of combination of radial velocities and proper motions for the stars. And various groups, in particular, some nice work led by Noyola et al. And Gephardt and others has led to the claim that there is indeed evidence in the dynamical and the motions of the stars in the cluster. There's evidence for a massive object, something roughly 10 to the 4, or a little bit more than 10 to the 4 times the mass of the sun. A reanalysis of these dynamics by van der Marel and Anderson and van der Marel that came out in 2010 based on the Hubble data seemed to indicate that their models really put a limit that was far below this 10 to the 4 solar mass estimate that had been put out there before. Sort of around the same time, there was a report, roughly about a year later, that perhaps there was evidence for a radio continuum source. And that radio continuum source was consistent with a massive object, once again, something 1,000 to 5,000 times the mass of the sun. But this was only an upper limit. It looked kind of compelling, but it's certainly not a surefire detection. I think we have some new radio data coming down the pipe soon that might help actually answer whether or not there is a convincing radio source there. I would like to point out in this context, though, that there's been a lot of shifting in the community about claims for intermediate mass black holes based on previous X-ray and radio detections. In particular, Laura Chumyuk and Jay Strader and others have been increasingly collecting simultaneous X-ray and radio data. There's a very nice piece of work by James Miller-Jones ruling out one of our really excellent candidates because the data hadn't been temporal, and so causation was not or correlation was not causation in those cases. And so these are a few pieces of work that have ruled out other intermediate mass black holes living in the centers of massive clusters based on new and interesting radio and X-ray results. So when we talk about the X-ray, we're really looking for some sort of signature of accretion. So some small amount of gas that is close to the intermediate mass black hole in the center of the cluster, and hoping to see some indication of what that accretion emission might look like. So we had looked at this before with a 70 kilosecond exposure from Chandra back some 10 years ago, and there was no X-ray detection within 5 arc seconds of the cluster core. We obtained in cycle 13 another 230 kiloseconds, putting us up to nearly 300 kiloseconds on the core of Omega Centauri. And I always try to give away the punchline early so that everybody can just relax and enjoy their lunch. There's still no X-ray detection even in this deeper data set. So I promised I would just show you at least briefly what the Hubble data looks like. So we actually have a very large mosaic of Omega Centauri. There was a mispointing here, and we never really filled in this gap, which is too bad. But these are some very, very beautiful data that tile the entire center of the cluster. We have H-alpha, R, and B imaging, and the total number of stars collected or detected inside of this mosaic was around 1.7 million. So it's really, truly a spectacular data set for doing some of these dynamical studies. Previous work had shown us that around 100, a little bit over 100 Chandra sources lie within the overlap between the Chandra and Hubble fields of view in the center of the cluster. And so the ACS sensitivity on the Hubble, the ACS camera on Hubble is sufficiently sensitive to do some really deep star counts and look for faint CVs and other good things. So one of the sources of confusion when you talk about the dynamical modeling and you try to compare it to the X-ray and to the radio has been that people haven't been able to decide where the center of the cluster is. So if you're going to search for something in the center, it would be nice if we could agree on a center. But that has proven surprisingly difficult. These are all X, 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 and circle, circle, circle. These are all various different claims for the center of Omega Centauri. And so I even show you within Noyola's own work that her own interpretation of the center has, this is the Anderson et al. Center. This is one from a first dynamical study, another from, I think this was actually the first dynamical study, this was the second. I've tried to mimic these three circles over here as well. Oh, sorry, these ones are backwards. I flipped the image around. Hold on, wait for it. There we go. Now they actually, these ones correspond to those three circles over there. So we searched all of these centers for the X-ray counterpart, but you can imagine if you're trying to look for the motions of stars within the potential well of an intermediate mass black hole, if you shift your center slightly off what the real center is, you might find funny, weird features and signatures. And so a lot of the disagreement in the dynamical community has come from disagreements really about this central position of the cluster. So kinematic fitting by Anderson and Vandermarle I mentioned, they tried various fits with and without an intermediate mass black hole, and found that a lot of their best fits do not actually require a massive object in the center of Omega Centauri, and in particular these are some nice chi-squared versus mass of the black hole fits, and it's just not the case that they really need a very massive object in order to fit the proper motion data for the objects in the ACS, the Hubble data. On the other hand, Noyola et al., as I've mentioned, do argue using their various different kinematic fits, and they even go back and use the same Hubble data. So they have continued to argue that there really is an argument for some sort of a massive object between 10 to the 4 and 10 to the 5 solar masses. And so we set out to test whether or not using just sort of very simple models for what the gas density in the center of Omega Centauri might be, whether or not we could put any constraints on these mass estimates. Okay, so just briefly to talk about the radio constraint, I mentioned that it was an upper limit, so these are the radio contours here overlaid on the center, and so the radio observations led to this estimate, something around a mass of the black hole somewhere in the range of a few thousand. But as we will have to do, it's not really clear what the efficiency, the accretion efficiency should properly be modeled as being in this setting. And so the deeper radio observations would be helpful.
How do you get a black hole mass from radio?
So they used the X-ray upper limit and the radio upper limit and used a sort of fundamental plane type argument to get a black hole mass here. Yeah. Okay, so that put G2, and so G1 is one of our other intermediate mass black hole claims, Omega Centauri. Here it is on the M sigma, the famous M sigma relation. So maybe it made Omega Centauri sort of consistent with other objects down here in the very, very low mass region. Okay, but what we wanted to talk about today was actually the X-ray constraints. So as I mentioned, our very early observations gave us an upper limit on the X-ray flux of an object that might exist in the center of the globular cluster. And our upper limit was a flux limit of about 4 times 10 to the minus 16, or a luminosity limit of around 10 to the 30. So then we added a bunch of really nice deep exposures, and this led to what is, I think, the deepest X-ray search so far for intermediate mass black hole in the center of a globular cluster. Oh no! I've already got a beeper. Okay, here we're just going to zoom in. This is our field of view. This is a ground-based picture of Omega Centauri. Here I've switched to a 3-color image in the X-ray. So this is optical, this is X-ray. You'll notice some weird emission over here. This is actually a background radio galaxy. So we're going to zoom in here into the center. These are CVs, well-known CVs. There's also a quiescent low mass X-ray binary up there. We're going to zoom in further. So now you're looking at X-ray data. These are various of these debated positions for the center of the cluster. Zooming in, zooming in. There's nothing there, in case you weren't sure what the moral of the story was. There's no source there. These are just pretty Christmas lights of X-ray photons with no actual detection. So taking the color off just to make this a little bit easier to look at, no matter which center we search, there's no X-ray source in the center of Omega Centauri. So a 6-count Poisson limit is about at the limit of our data here in the central regions of Megased, and this corresponds to an upper limit in the X-ray around 1.6 times 10 to the 30 ergs per second. We did search a very large 6 arcsecond error circle for all of these different central positions because it's possible an intermediate mass black hole may actually wander around in the center of the cluster sort of due to Brownian motion. And so we did indeed search over a fairly large area. Okay, so since time is short, I'm going to skip over some of these different things and just say that we use this using some very simple accretion models and a very simple model about how much gas we would expect in the center of Omega Centauri just due to stellar winds. And this is a plot of the accretion efficiency versus the black hole mass, where what I'm showing you here are in the gray boxes the limits that we can place based on the X-ray data alone. This is using a model from Tom Macron and Matthew Servelat. So we can rule out this whole part of parameter space for the sort of more massive end of an object in the center. These other lighter gray bars are just representing even sort of more simplistic accretion models. And the things that I'm showing kind of vertically here are different dynamical mass estimates. And so basically what this tells us is that we are confined to being in a region of extremely low accretion efficiency if we have a massive-ish object in the center of Omega Centauri. So for that 10 to the 4 number I keep throwing out there, you're talking accretion efficiencies of like 10 to the minus 8. So incredibly low accretion efficiency if this object is in fact massive and living in the cluster. Okay, similar efforts have been made. I'm going to kind of skip through this just because of time. And just give you my, well, maybe I'll go back to it very quickly. We can do the same exercise using that radial upper limit and plug our X-ray data in and do the fundamental plane calculation ourselves. And we can, from that, get a lower limit on the intermediate mass black hole. The mass of the intermediate mass black hole is around 10 to the 3 solar masses. So this is not a particularly strong constraint, obviously, but it doesn't really look like there's any indication of an accreting supermassive or intermediate mass black hole in the cluster. So this is just summarizing what those flux limits are, and we can more or less rule out, unless we have some sort of really bizarrely low accretion efficiency system, we can almost rule out a 10 to the 4 solar mass black hole based on the X-ray signatures, and I note our assumptions about what the gas density is in Omega Centauri. Okay, so that's where we left it in 2013 with the work that we did from Chandra. But I noticed from this last, so this is now switching into Laura Watkins' work, not my own work, but I just want to throw out there that a few weeks ago she introduced us to this new modeling that she's doing based on really beautiful proper motion data. I don't know whether or not people are aware, but we actually use Omega Centauri as a calibration field for HST. So we go back and we visit Omega Centauri all the time. And so we have amazing proper motion data that we can pin to this incredibly deep mosaic that we made way back when. And Laura has been working very hard to try to look once again dynamically based on proper motions for a massive object in Omega Centauri. And here's her histogram now of the likelihood, the numbers of stars here pointing to a mass of a particular dense object in the center of the cluster, and she finds very, very convincing evidence based on the motions of the stars for 25,000 solar mass black hole in the center of Omega Centauri. And so, as Laura said at the meeting, she has tried incredibly hard to get rid of this. She doesn't want it. She didn't want it. She works closely with Jay Anderson, who said many times it's not there. So there's a higher likelihood up here. These ones are showing that there is some sort of intermediate mass black hole. These would be a tracer of none. The fast-moving stars near the center really prefer a black hole. And so I would just say, oops, sorry, that was slipping on. I would just say that the jury was really still out. We seem to have a lot of tension between the accretion type diagnostics for these intermediate mass black holes in massive stellar clusters and the dynamical work. And what I would like to see going forward is a better measure of the gas density, an empirical measure of the gas density, not just one based entirely on the assumption that stellar winds are contributing to gas that should be accreting onto these systems. Because pinning our accretion models to an assumption about the gas densities in the cluster, I think, might be guiding us in the wrong direction. And so there's been a lot of discussion about how we can do that in these very, very, very crowded fields. So I'll leave it there.
You can use your upper limit to actually constrain, for example, the dark matter plus annihilation models of winds. Since this object is thought to be the core of a galaxy that was stripped, you should have dark matter in it. And that's another, since you get very deep into the X-rays, you can put probably tighter limits than anyone else on the central cusp of the dark matter.
Good. Yeah, let's talk about that more. That would be fantastic to do.
Sayan?
So I was confused by one thing.
Yeah.
So I understand both your X-ray and the ATC radio are upper limits.
Yeah.
But when you combine them, how do you get a lower limit on the black hole mass?
It just has to do with the way the fundamental plane calculation treats the two. So you have the X-ray and the radio. They just end up. You see it. This is a negative. You're working in log space, and you have a negative here. So you basically have an inverse relationship between the two of them.
But it's also assuming that it's a detection.
That's right. Exactly. You're taking the upper limit as if it were a detection, right? And
You
so,
don't detect anything.
you don't detect anything. This is we're just trying to fool around with, like, okay, what about if it was sitting just below our detection limit, and then what could
So
we
this
say?
is actually an upper limit on the mass.
Yeah.
We can talk about this after. It actually really does give you a lower limit on the mass. Some of the other things, so these are giving you upper
Either
limits
doesn't
on the mass.
exist, either there is nothing, or the mass is above 10.
That's right.
That's what it is.
Yes. I know it seems, I wrestled with this when I wrote the paper. It's very counterintuitive, but it is indeed a lower limit on the mass.
We need to move on because we are going beyond our time limit. Thank you very much, Daryl.
I'm going to just use my brain. Take this first. To advance your slides, and also the way you learn won't work unless you
James, is that your dark year?
Okay, wait, it's a different, actually, all right, let's do it this way. Okay, great. So I'm going to describe something related to the cosmological gamma ray burst, the long duration variety. And this is work done with my former student Paul Duffel, who's now at Berkeley. And it's something very interesting that was in the data before, but we've kind of appreciated its significance. So let me just remind people the basic idea in long duration gamma ray bursts is they come from massive stars, and that may be surprising because they're ultra-relativistic sources. And the way they can work is that a gamma 100 jet can burrow its way out of a star by shocking the star and pushing it into a cocoon that surrounds the jet core. And then the question is what happens afterwards. What we demonstrated a while ago is that you could get a relativistic jet out of a star, and it expands far away from the star and produces a GRD. But there was an issue. If you can notice it at the very top, that green blob. And the question is, what happens to that? Okay, so that's what we called originally a plug, and we were a little concerned. This is the core of the jet. It's moving very fast. But there's a little blob. This is an older simulation. But then when we did it again, a few years later, we saw it. It's a little bit hard to see, but there's an overdensity of the kind of light yellow that's in that red circle. So there is a relativistic jet core, but but it's pushing ahead of it a denser blob. Okay, and so you can see this here. It's kind of nice. This is forming a cocoon, but you can't see it because of the color stretch. But there is a little plug of material that's being pushed ahead of the jet. And there it is. You can see that little piece. And when the jet breaks out of the star, you see that little yellow disk. So that might be an effect of 2D. This is an axisymmetric simulation. But when later Zhang went back and looked in 3D, and what you find is the jet meanders a little bit, only if you perturb it. But it always develops a little bit of a cap, that we call it. And then even there's a little bit of red in front. So as the jet breaks out and accelerates, it becomes relativistic. And that material simply causally can't travel sideways. All of its motion is boosted into 1 over gamma. So it's stuck in front of the jet. So what you have then is a relativistic jet which can expand and produce gamma ray emission, the prompt emission. But it's got that thing moving slightly slower, like 0.999c, 0.995c. So they're both moving at the speed of light, so it stays ahead of it for a while, but ultimately they're going to collide. And so what we've done is use a new technique. So this is a technical slide showing you that we have what's called a Lagrangian scheme to solve the equations of hydrodynamics. And essentially, all these radial faces of the grid, which is a spherical polar grid, move radially outward with the flow. So we can solve for something that starts as a star way at the middle here, and then follow this shell of material and the mesh moves with the material. So it can expand many orders of magnitude and radius. And what we did is, so we redid these simulations of jets breaking out of stars in a 35 solar mass main sequence star, which was 18 solar masses when it died. It was rotating almost maximally, and it had a low metallicity. So this is its density structure, which we fit with this formula. And we put it in a wind medium, which is going to be important. Okay, and then I don't want to go through all of this, but this just describes the parameters of the star. And then we have an energy to mass, an eta of 100. So this is a jet that should asymptotically have Lorentz factor 100. Okay, and then we powered the jet for 10 seconds, which is the duration of a long duration gamma ray burst. That could be 100 if we wanted. So here shows what happens. And it's Lagrangian, so it's funny. It looks like nothing's moving, but it's actually expanding by many orders of magnitude. So we're deep in the center of the star now, and the jet is starting to flow. And on the left, you can see the density, and on the right, you can see the Lorentz factor. Now it's broken out, but notice that there's something really interesting. And there's the radial coordinates coming through. When it breaks out, there still is that little cap of material in front of it. And this is ruined by the movie. In fact, it's much higher resolution in reality. Okay, but then now we can follow it even further to the afterglow stage. So now we're picking it up, and if you can look, it's expanding so its Lorentz factor is 100. You can see on the top, on the left there, and it's expanding. Now it's at a few times 10 to the 13 centimeters, and you can see here that it's building the shell on top of it. If you can see, have really good eyes, you can see that that shell is really Taylor unstable, so it's becoming turbulent. But the main point is, as it travels through space, it has a slower component in front of it at all times. So you have a relativistic shell of gamma 100 with a gamma 50 shell that's stuck in front of it. Can't get out of the way. And so now we followed it all the way until the afterglow stage. So this is the scale of 10 to the 7, almost a parsec. So it's gone from 10 to the 7 to 10 to the 17 centimeters. Almost a parsec. Okay, and so what happens here is you can see the different phases. So that's inside the star at 1.5 seconds, breaking out of the surface of the star, and this is the surface of the star. So it's broken out, and now it's expanded and expanded and expanded. And this is the thin shell that forms, and that's going to drive a shock wave into the ISM that produces the afterglow radiation. So this clearly shows that. It's too bad I can't point to it. But on the left is Lorentz factor. Left is density, and right is Lorentz factor. So the main point is the red on the right-hand panel. That's the gamma 100 material, and the yellow is what we're calling the plug, or the shell, that's ahead of it. So that has a gamma of 60. So gamma 100 and gamma 60 in front of it. And on the left, you can see the density. So that it's a denser shell by only a factor of a few. So it's higher rest mass density, lower Lorentz factor. And so these things are going to collide. They have to. And so here's a cartoon to show you the basic idea. So you have a ultra-relativistic jet, and it's got this shell in front of it. And that always has to happen. So what we expect to happen is eventually, this thing is going to collide with the thing in front of it. And so what that'll do is it'll send a forward shock into the shell and a reverse shock to decelerate this jet core. After that reverse shock travels through the relativistic jet core, it's going to have a lower Lorentz factor, let's say gamma 30. And so that is really interesting because that means that the jet after this internal collision will be more baryon loaded. So it's a lower Lorentz factor, just gamma 30. So that has to sweep up more mass to decelerate. Okay, it's just got more momentum. And so what that does is it just travels along without decelerating, driving a forward shock in front of it. And then much later than usual, it eventually transfers its energy to a shock. So this tan color is shock to material. So the key difference is before people thought you just had a gamma 100 jet, it produced prompt emission, and then transfers its energy immediately with ISM into a shock, which produced the afterglow. What we find is that's not true. It first has to deal with the shell in front of it. And what that means is that very much later you go into the Blanford-McKee phase. Okay, so this is dynamics, and again, I think it has to happen. And so this shows the basic idea. The jet breaks out of the star, and this is the maximum Lorentz factor and the average Lorentz factor, and it accelerates to gamma 100, and then it coasts, but then it collides with the shell in front of it at 10 to the 4 seconds. And that decelerates the maximum Lorentz factor down to 60. And so that coasts for a while until this time, and then goes into Blanford-McKee, into this external shock. Okay, so that's the dynamics, and we're very confident that this is right. So then the question is, and by the way, we weren't trying to produce any model for anything. We just were curious about what the physics of this explosion should be like. But then we put in a radiation model, and we just used standard synchrotron parameters to model the emission that you see from this relativistic flow. So we save all the data from the hydro simulation, and then we know the emissivity of each fluid element. We sum that up and calculate a light curve. That's what we do. Okay, and this is what we get. So this is the early light curve, and plotted underneath it is a swift gamma ray burst 110312A. These are the data points. And so what happened is at late stages, we got this kind of Blanford-McKee evolution. But at earlier phases, we got a plateau, and before that, we got a steeply declining spike. Where did this come from? This line here is the emission of the internal shock that's decelerating the fast jet core. And this line here is the external shock that's being driven into the ISM. When we add them together, we get a steep decline, a plateau, and a transition to Blanford-McKee. The coasting phase, this starts when the shock has passed through it. That happens at about 200 seconds, and the coasting phase lasts for about 10 to the 4 seconds, as you saw before.
How much is the mass in the shell?
It's about twice the mass in the jet. And I'll show you the density again in a second. So basically, so here's the story. But it's not optically thick, if that's your concern. So this shows it again, just showing the different pieces. This collision causes the internal shock, which causes the sharp decline. The coasting phase, so normally that would go straight into Blanford-McKee here, but because it's baryon loaded after the amalgamated jet forms, it coasts for this time period. And that is a declining plateau, if and only if the gamma ray bursts happen in a wind medium. And that's in fact what we expect for gamma ray bursts that are formed by massive stars. They have winds, which they blow, so the density environment should be 1 over r squared. And that's what we put in. If we put in a constant density, the plateau would be rising because this amalgamated jet would shock more and more material and it'd get brighter and brighter. But if the density is declining like 1 over r squared, like is reasonable, then we get a plateau that's declining, and the slope, in fact, matches this observed part, and then it enters Blanford-McKee as you'd expect. And again, we didn't try to fit this burst at all. We're just overplotting what we got with the burst that we picked. Of course, we picked one that looked as nice as possible. But other ones look like this as well. Okay, so there's other predictions of this model. One is that we can also predict what the optical slope should be in this frequency regime. And we get, for electron index of 2.5, that the difference in slope between the optical and the X-ray should be a half. This is in contrast to the external shock model by multiple people, which would predict a quarter. So what we think is that people should look at these slopes and compare them, and that might distinguish between these two models. And this type of data, this is a paper by Zanoni et al., 2013, where they plot alpha X versus alpha opt. And some numbers are just crazy, but some do appear like they might distinguish between these two models if you had enough good data. Okay, and so the last thing I wanted to mention, we pointed out that Rayleigh-Taylor instability is that these things are also Rayleigh-Taylor unstable, and that's very important for generating magnetic field in order to produce the emission that we observe. And that's, so gamma ray bursts in general are Rayleigh-Taylor unstable, and that's just because of the structure where you have a forward shock, reverse shock, and contact continuity. That's notoriously unstable, but since we have this moving mesh, we're able to resolve that and show what we got. So the conclusions are jets have to be top heavy. If a jet breaks out of a star, there's always a little matter at the front. When the jet accelerates, that is causally forced to be in front of the ultra-relativistic jet core. The internal collisions slow down the jet core later, which gives a steep decay. The coasting amalgamated jet causes a plateau. And the decaying plateau implies that there has to be in a wind medium. We predict delta alpha between the optical and X-ray slopes to be 1/2 in contrast to 1/4. And just to remind everyone that jets and particles are Rayleigh-Taylor unstable, and that might be a way to generate magnetic fields. Thank you.
Beautiful work, Andrew, and you can produce also variability, not just.
Yes, of course,
We
yes.
have time just for one question, so
Okay.
since Ido raised his hand first.
Sure.
So one prediction of this model is that you will have essentially two reverse shocks, right? There's a reverse shock from the first interaction and then
Yep.
one with the interstellar medium.
Mm-hmm.
And so are you able to produce light curves of what that might look like? Because I think
Yeah.
we have data on that.
Well, let's talk, because yes, absolutely, we can calculate the light curve. Yeah.
We need to move over to the next talk
Okay.
because we don't have much time. Thank you very much, Andrew.
Can you hear me? Okay, so I'm going to talk, I guess, about the interaction of planets with their host stars. And the main point I will try to mention is that when we consider habitability in planets, we should consider also the physical environment at which these planets reside in, not only the radiation environment which produced the conventional habitable definition. Habitability. We all know that the habitable zone of M-dwarf star is very close to the star itself, so we can detect these planets close to the star. However, we should consider that stars produce stellar winds, which is this continuous outflow, radial outflow expanding from the star, and this wind can affect the atmospheres of the planet. And if the planets reside very close to the star, the stellar winds can be extreme, and we should consider this interaction in the context of habitability. The Earth or magnetized planets have the strong magnetic field that protects them or protects the atmospheres from the erosion by the stellar winds. Mars does not have a magnetic field. We believe that Mars lost most of its atmosphere due to the erosion by the stellar wind over time. And we have Venus, which has a thick enough atmosphere to sustain this stripping by the solar wind. So we can consider all these effects. So if we want to simulate all that, we can have one model for the stellar corona, and the stellar wind to predict the wind. We can pick an M star. In the case I will show you, this is EV-LAC. It's an M3.5 star. This is a star that we have observations of the surface magnetic field that we need to drive the simulation. And we can produce a solution for the stellar wind and use that solution to drive a local model around the planet to study the interaction of the planet with the stellar wind. Here I'm going to use 3 potentially habitable planets that were identified by Dressing and Charbonnet. Here you can see the solution for the stellar corona magnetic field. The surface field is shown on the sphere. And this is the equatorial plane displayed with the dynamic pressure of the wind. And the 3 orbits of the planets are shown in blue circles. The nearest planet is at about 0.6 AU. The second one is 0.85 and 0.15. And one thing I would like to draw your attention is this solid white line represents the Alphen surface. This is the point where the stellar wind achieved the Alphen speed. And you can see that the orbits of the planets cross from the subalphenic to superalphenic plasma environment. And this will be very important for the results I'll show you. So let's start with magnetized planets like the Earth. I took an Earth-like, or typical parameters of an Earth-like planet. And here I show again the equatorial plane. And again, I would like to draw your attention to this crossing of the subalphenic regime to superalphenic regime. This is the orbit of the nearest planet that I showed before. And you can see that when the planet resides in a subalphenic plasma, the magnetosphere of the planet looks like that. You can see that there are 2 standing lobes of magnetic field above and below the planet. And this is a typical configuration for a body moves in a subalphenic plasma, just like Io, the moon of Jupiter. And this topology is called the Alphen wing. It's a typical configuration of a conducting body moving in a subalphenic plasma. But when we move to the superalphenic regime, you can see that we have a ball shock build up in front of the planet. The field lines are draped behind the planet, and this is a typical configuration for a magnetized Earth-like planet sitting in a superalphenic regime. Now this orbit takes about a few days, so it means that this planet, the topology of the magnetosphere of this planet dramatically changes along the orbit, and this change in the magnetic field topology can drive Joule heating at the top of the atmosphere. And here I show I calculate the Joule heating of these 3 planets. And for reference, I also calculate the Joule heating for the Earth during quiet time or ambient solar wind, and during a coronal mass ejection event which hits the magnetic field of the Earth and kind of shake it. And you can see that there's 4 orders of magnitude difference between the ambient Joule heating in the nearest planet and the Earth. And if I also did a time-dependent simulation that I moved the planet from the subalphenic to the superalphenic regime, and there's an increase of even another order of magnitude in the Joule heating. The units here are a little bit different, but there's another order of magnitude between here and here. So there's a lot of Joule heating coming from the top to the top of the atmosphere of these planets. As a result of the interaction with the stellar wind, and of course it affects the atmosphere. Now what happens in a non-magnetized planet? Let's assume that we have a Venus-like planet, and the simulation I will show is based on the simulation of Venus performed by Maitel in 2013. Here we assume a neutral atmosphere composed of oxygen and CO2, and the major ions are O+, O2+, and CO2+, produced mostly by UV photoionization. This plot shows the 3 planets from top to bottom, and each pair has a subalphenic solution and a superalphenic solution. And for reference, I show a solution for Venus here, and Venus that I set at the orbit of Mercury. So what I call Mercury, it's actually a Venus at Mercury's orbit. This plot shows contours of the ratio between the oxygen ions and the hydrogen ions. And you can see that for the subalphenic solutions, this enhanced density of oxygen is confined to the equatorial plane, or for the subalphonic regime, it's actually to produce these lobes that we saw before. This is again a confirmation of this alpha wing shape. Here in the Mercury subalphonic case, it's a little bit like that as well because of the very low Mach number for this particular case. This plot shows the density structure of the atmosphere. The y-axis shows the altitude, and the number density is shown on the x-axis. Essentially, these lines represent the stellar wind hydrogen ions, and these are the atmospheric ions. And you can see that the stellar wind penetrates all the way up to about 1,000 kilometers above the surface. This is really deep into the atmosphere. The peak of the atmospheric ions is about 500 kilometers. Here in this plot, I show the deceleration of the stellar wind as a function of altitude above the surface. And you can see that here, for the subalphonic case of the nearest planet, the stellar wind is stopped at very close to the planet, at about few thousand kilometers. This solution is showing the deceleration for the magnetized case, and you can see that the magnetized case is the stellar wind is stopped much further away than the case of the non-magnetized planet. Here on the right, I show the effect of the enhanced UV radiation as a result of the close proximity of the planet to the star. Essentially, the difference between the black curves and the red curves show the case where I did not increase the UV, or I did not scale the UV flux with distance, and the case that I did. And you can see that the enhanced UV flux generates more ions from the atmosphere that push away the stellar wind to about 200 kilometers higher above the surface than the case without the scaling of the UV flux. And finally, I did a crude estimation about the total mass loss of ions from the planet as a result of the UV radiation and this interaction. And I calculated a lower limit of about 10 to the minus 11 Venus atmosphere mass per year. But I would like to state that this model does not account for the acceleration of these ions in the atmosphere. It's simply they just created and kind of follow the single fluid plasma velocity. But if we do account for that, we can get about 1 to 2 orders of magnitude higher mass loss rate. And this means that over a course of 1 billion years, we can lose the planet can lose all of its atmosphere, or significant amount of it. So in conclusion, the stellar wind conditions and the space environment at close orbits are very extreme, and we need to take that into account when we think about planet habitability. Oops, well, it's everything. The atmospheres of magnetized planets should be sustainable over time, but there's a lot of heating, joule heating that is generated as a result of the interaction of the magnetic field with the stellar wind. But for a non-magnetized planet, even with a thick atmosphere, we should expect that significant amount of the atmosphere will be lost over a course of about a billion years. And that's it.
Perfect time. James?
So Earth's magnetic field flips periodically, and when it does so, it decreases in strength for some amount of time. Presumably the mass loss rate during those periods is a little bit elevated. Does that win out over, say, the average mass loss rate when the magnetic field is on?
The duration of the flipping is very short comparing to the stable stages. Talk about 100,000. The flip every roughly 100,000 years. The flip itself occurs within like less than 5,000 years, I think. So yeah, there should be the transitional stage at which you could lose more mass. But I think on average it doesn't matter much. But yeah, something to consider as well.
It looks like we reached our time limit. Thank you all. That's it for now.
All of us
That's mine. This is theirs. I'm here all day tomorrow. If you have a chance, we should chat. Yeah, okay. Okay. That'd be wonderful. Okay, great. Very nice talk.
So you kind of solved everything.
How much is the confidence interval?
So in this model, it's completing the effect of the use on the atmosphere beside the ionization. So